Hello ladies and gentlemen, so this is going to be the lab exercise for the Kruskal-Wallis test. So you'll remember in the previous lab video we went over the parametric focus test, so the analysis of variance, which is all very well and good if you've got normally distributed data and you've got data with equal variance in the population and you've got interval and ratio based data, but that might not always be the case. So for example, if your data don't conform to those assumptions, then we're going to have to consider using a non-parametric test, for example, like the Kruskal-Wallis test if you've got 3 or more samples. And what we might need to do is we might need to downgrade that continuous interval data so that it then forms ordinal ranks, essentially. Let's just do this now. So you'll remember from the previous session we have this data frame. So we've got the 4 sample groups which all have house prices. So we've been out and we've sampled different house prices and then we've put them into a data frame here. So we have group 1, group 2, group 3, group 4, and we've got the house prices. So for group 1, we've got values from $138,000 all the way up to $184,000. Okay. And what we're going to do first is we're going to use this inbuilt rank function. So if you look here, we are able to get the sample ranks of the values in a vector. So what we're doing here is we're saying give us the sample ranks for the prices, and then basically allocate that to a new variable within the frame1 data frame, but call it ranks. So when we do that, that's essentially how we're able to create this column over here, which basically provides the ranks. So from the smallest house price, which here is actually in group 3, all the way up to the largest house price, which is in group 4 and is $210,000. So just before we get on, let me just recap on what we were doing in the lecture with the Kruskal-Wallis test. So I've just improved the slides now so that the master slides which you receive are a little bit clearer than the ones that were used in the previous lecture. So the main calculation for the H test statistic is this one just here. And the difference is that this one, which is longer and arguably more complicated, it actually has a denominator which contains the correction factor for where you've got tied ranks, which is necessary when you've got more than 25% which are actually tied. We're not going to go over this in the lab, so I just wanted to just remove this from the cognitive load which we're going to need to be mindful of as we move through this week. So we're going to focus just here on calculating the H statistic. And you'll remember that essentially we had this set of steps that we needed to go through. They're quite similar to the Wilcoxon steps that we had to go through when we're dealing with ranked data. And what we've done so far to our house price data set is we've combined all of the observations into one single list. So all K samples have now been put into a data frame. What we then have done is we basically ranked all of those observations based on the values for the house prices. Essentially what we need to do now is we actually need to sum up these ranks for each one of the samples so that then we're able to go back to the equation and solve it. So essentially what I've got here is just a little piece of code which basically just says, can you sum the ranks for all of those observations which are in group 1. So this looks complicated, let's just break it down. So just imagine that the sum function is just able to add together whatever you put in here. So I've just put 2 numbers, would sum together anything that you put within here. So that's fairly straightforward, I hope, for you. As you know, we have this variable which we just created within the data frame called ranks. So if I call that, it's now printing to the console all of the values for the ranks that we have. But we don't just want all of the ranks for R1. What we want is just those ranks which are actually in group 1. So if we go back to the data frame, and we've got the group just here, so we've got 6 values, and ranging essentially from 138 all the way up to $184,000. And what we want to do is we just want to sum these ranks for the first 6 rows here in order for us to get the sum of the ranks for just this one group, so just this one sample. So what this is doing when you add in this extra little bit is it just is indexing into that data frame and just going to the group variable and saying I'm just going to give you the ranks for those rows that are part of group 1. Okay, so these numbers here now should be basically the same as those ranks that we've got here, so 12, 5, 3, 9, 17, and 6. You can see that they're the values that have been printed to the console. So I hope that that is straightforward to you now. When you see a big function like that, the way you need to approach it is to break it down into lots of smaller parts so that you're able to understand exactly what's going on. Great, so now you know exactly what I'm doing here. I'm going to create the sum of those ranks for the 4 different samples. So we can see R1, R2, R3, R4 just here with all of the sum of the ranks. And there's quite a bit of variation, you see. So from 27 all the way up to 108 in R2. And then what we want to do is we want to put all of those rank sums into a vector, which we're going to call all R. And we're going to sum all of the observations that we have within our samples, which is 22. So we covered that previously in the ANOVA example. And now basically we've got all of the required inputs that we need in order to calculate the H statistic. So we've got the all R vector, which contains the sum of the ranks. We've got the number of total observations across all of the samples. So if we just go back to our slides just here, so the H statistic, basically we need to divide 12 by this denominator just here, multiply it by the sum of this component here, and then subtract this final component. Okay, so what we're doing is we're going over the first component just here. So it's 12 divided by n multiplied by n plus 1. Okay, and then we're going to sum all of those, all R values squared divided by all n. So we have the sum of the ranks of the samples, and we have the number of observations in each sample. And we're going to sum all of those. And then finally what we're going to do is we're going to subtract 3 multiplied by n plus 1. Okay? And then hopefully when we do that, we end up with H statistic, which here is quite large, 10.465. So then we need to basically get a p-value for this H statistic. So what we're going to do is we want to be able to provide this value and then have the quantile return. So particularly for the distribution, the chi-squared distribution that we're using, we have this one function that I covered within the lecture, which basically provides the non-central chi-squared distribution, or allows us, using as we've done for other similar distributions, to use this function in order to obtain the p-value. So you need the PCHISQ function, which you can read more about here. And when we do that, we end up with a p-value which is really quite low and is significant. So at the 95% confidence level, this value is below 0.05. So we know that we've got enough evidence to reject the null hypothesis, essentially. So when we consider the house price samples that we've got, we're able to conclude that they've come from at least 2 separate populations, essentially, because there's quite a significant amount of variation within those samples that hasn't just occurred by random chance. And we've calculated that p-value now. Let's just have a look at how we would automatically generate that test statistic. And you can see that if we do that here using the Kruskal.test function, and we provide it with the price and the group data, essentially we are able to obtain a chi-squared value which is pretty much similar to what we've got. So 10.465 up here, we've got 10.471 down here. We've got a p-value which is again pretty similar, so 0.0149, which is the same as what we've got up here for the same number of significant figures. So that concludes this laboratory today, and what we've done in both of those examples is we've calculated by hand exactly how exactly the steps for us to produce those test statistics, and then we've been able to validate that procedure by comparing it against the automated generation of those statistics using some of the inbuilt functions in R. So now in the future, if you need to come back to these tests, you know, once you've passed this class and you go on and do research elsewhere, essentially you will be able to just use the inbuilt tests and hopefully have a good understanding of what's being carried out within the code behind the scenes that R just basically runs through those calculations automatically and produces those answers for you. So if you've got any further questions, don't hesitate to get in contact with me, and I'll be glad to help you. So I hope that this has been useful for you. If you still got queries, then take a look at the videos again, read the book, make sure you go over the lecture slides in tandem with this code, and hopefully that will help to cement your understanding of this particular topic. Thank you very much for joining me, and I'll see you again soon. Thank you.